Good morning, folks. Today we're going to talk about Sommerfeld quantum numbers, the quantum numbers L and the quantum number M. We're not going to deal about the power of those two quantum numbers. You'll find in the internet many videos that will talk about the utility that those quantum numbers had in the success they had in the developing of the atomic theory. What we're going to see today, or try to see today, is how Sommerfeld came out with the hypothesis of the existence of these two quantum numbers, and also, especially, how he came out with the rules that are behind those two quantum numbers. I recall to you that those rules are pretty weird. Quantum number L is set to assume only integer values that span from 0 to n minus 1, where n is the Bohr quantum number, the principal quantum number. And quantum number M, again, has integer value, and it spans only from minus L to plus L. So what we'll try to see is how Sommerfeld came out to this conclusion without using the advanced math Sommerfeld had to use. I want to point out that this is not an alternative way of getting to those two quantum numbers. The only way is the Sommerfeld method. What we'll try to see is a way to visualize the logic that's behind those two rules without using the math. So in order to do that, let's move to the chart we'll see here. So what do we see here? Here we see the electron moving around the nucleus in what is called the ground state. So this is the state that's described by Bohr in the case of the lowest energy possible. So the quantum number, Bohr quantum number, is n equals to 1. What does Sommerfeld say? Sommerfeld says we should not rule out the possibility of having also elliptical orbits as opposed to only circular orbits. But this can happen only when n gets higher, because in this case, when n is equals to 0, we can only have, nothing can be shorter than this radius. But when n equals to 2, like in this case, when n equals to 2, we can have an elliptical orbit where the minor axis still remains with the lowest possible value and the major axis goes to 2, or we can have the circular one where both minor and major axes are the same. And the same thing happens with 3. When n equals to 3, we can have again this ellipsis, this one, and then we go to the circular. And when n equals to 4, again, this case, second ellipsis, third one, and then we have the circular. So let's go back to the case where everything is 2. What can we say in this case? In this case, we say that when the angular momentum is the lowest possible, so the power of rotation is the lowest possible, the electron cannot just swing like this. It has to move around this ellipsis because it can't get closer to the nucleus than this radius. But when we have a higher energy, we can also have a second angular momentum, a higher angular momentum that actually gives origin to the circular orbit. So this is the case where the angular momentum L is 0. This is the case when the angular momentum L is 1. And we go moving forward. In this case, n equals 3. This is the case when angular momentum L is 0. Angular momentum L is 1. Angular momentum L is 2. So as you can see, anytime we have a number n, we can have angular momentum 0, 1, n minus 1. See, and 4, n is 4, L is 0, L is 1, L is 2, L is 3, so n minus 1. So that's the reasoning we can follow to assume this strange rule for quantum number L. Now let's see what we can say about quantum number M. So in order to go to quantum number M, let's move to this chart again. Let's look at these two orbits, the yellow one and the green one. So far we're looking everything on the two-dimensional level, like in this drawing. So we are looking everything in this x and y plane. But what happens, so forget about this green one for the moment. Let's focus just on the yellow one. What happens if I assume that the green one, which I recall is bigger than the yellow one, can be tilted along this direction in the third dimension? Let me show you what I mean by going to this heuristic example. Let's look at what we see here. If I take something that is almost circular, like this one, sorry, look at the shadow. As soon as I tilt it along this direction, if you see the shadow, the minor axis gets smaller and smaller. The major axis stays the same, and the minor axis gets smaller and smaller. Even it can go all the way down to 0. See? So let's see what we can say about this, looking back to the drawings. In the drawing here, we see that if we tilt the green one, we can have that the minor axis eventually, which is bigger, eventually seen from the top, is as big as the yellow one. Let me show you with this case here. So here we have the case where the minor axis is the minimum possible. Then we have the yellow one. This is the case where the green ellipsis is not tilted at all. But I can assume I can tilt it this way so that the minor axis, once is projected onto the xy plane, is actually equal to the yellow one. And again, in this case. But this is the case where L equals 1, remember, the green one. So when L equals 1, I can have this case, which is called M0, this case M1, and this case M minus 1. When L equals 2, like in this case, that's the case where M equals 0, M equals 1, when the projection is on the second smallest, minus 1, of course, the other direction, 2, when the projection is on the smallest, and minus 2, the other way. So in this case, we can see that when L equals whatever it is, M can have values that span from minus L to plus L. So that's all it is to try to visualize sommerfeld quantum numbers. They were extremely powerful quantum numbers. Like I said, they solved practically all problems of atomic spectra and atomic physics, except for the Zeeman effect, for which we had to introduce spin. I hope you managed to see the logic that's behind it. I hope this is easy to understand, and I hope you enjoyed it. See you next time. Bye-bye.